Hello students, this is Mr. Allen here. Today we are going to move on in chapter 3. Last week we looked at section 3.3, which was on increasing, decreasing, and the first derivative test. So everything was based on the first derivative. This week we're going to look at what the second derivative does for us, and that's going to be concavity in the second derivative test. So our objectives today are 3. Determine where a function is concave up or concave down. Find any points of inflection. So we'll have to define what those are, points of inflection. I guess we should probably define concavity, which is probably a new word to some of you. And we also need to apply something called the second derivative test to find relative extrema. So first of all, what does this concave or concavity word mean? Let f be a differentiable function, then a graph f is called concave up if f prime is increasing. If f prime is increasing, it is called concave up. Let me get my highlighter here. So if f prime is increasing, it's concave up. If f prime is decreasing, we call it concave down. Let me show you what I mean by that. So here we have the graph of a function. It kind of looks maybe like a parabola. But what I want you to notice is this. Anywhere on this curve, first of all, you'd agree it's, we will call this concave up. So it's caving upward, if you will. Anytime we draw a tangent line on this curve, you will notice that the tangent line is below the curve itself. This is concave up. F lies above all of its tangent lines. Similarly, if we have a curve like this one that's concave down, then you'll notice that all the tangent lines lie above. So we say that f prime is decreasing. Now, this is the most important slide of what we just said. So the last slide gave us the definition of concavity. This slide tells us how to test for it. So I'm going to be asking you, find where it's concave down, find where it's concave up. So this is the most important slide based on concavity. So if we know a function has a second derivative, if the second derivative is greater than 0 for all of the x's, then it's concave up, which is nice. Just like in the previous lesson, if f prime was greater than 0, we said the function was increasing. Here we're saying if the second derivative of the function is greater than 0, then it's concave up. Similarly, if f double prime is less than 0, we say that it's concave down. Let's look at an example of actually doing that. It says determine the open intervals for which the graph of f of x, which is 6 over x squared plus 3, is concave up or down. So first of all, notice that this function is defined for all of the real numbers. So you can put any value of x in here and you will get out another real number. So it's continuous and it's going to be differentiable. So that's great. So let's go ahead now. We got to work for the second derivative because we're worried about concavity. So we're going to be interested in f double prime. So here's one trick that we can do. Instead of using the quotient rule on f, what we could do is we could just take that denominator and move it to the top and make the exponent -1. Since we're doing it that way, we don't have to use the quotient rule. We can simply use the chain rule. So the outer function, if you will, you could think of this as 6u to the -1, right? So this is the outer function. The inner function would be x squared plus 3. So now we can do the chain rule. Applying the chain rule, we leave the inner function alone. We do our power rule, and then we do the derivative of our inner function. We can then simplify that by bringing this x squared plus 3, which is to the -2, to the bottom. So this is f prime. But this is just the first derivative. Since we're interested in concavity, we're going to go and go to the second derivative. Now I'm going to go ahead and use the quotient rule. And just a quick reminder, the quotient rule is low d high minus high d low over low squared. So that's what we did here. I've shown all the work if you want to check that. Let's clean it up a little bit. The numerator becomes 36x squared minus 1. The denominator is x squared plus 3 to the third. So now here's a crucial step. Because f double prime is equal to 0 when x is equal to plus or minus 1, which hopefully you can see that. In fact, let me go ahead and just write that down. Let's do that in a pen. So f double prime, when does that When does that equal 0? Well, when x is equal to plus or minus 1. F double prime is defined on the entire real number line. So we need to test from negative infinity to negative 1, from 1 to negative 1 to 1. I think I got that backwards. I'm sorry. This here should be negative 1 to 1. So let's mark that out. That's a typo. And then finally 1 to infinity. So we're testing, again, let me emphasize this. We're testing from negative infinity to negative 1. That's all the way up to here. Then we're going to test, let's do red here. Now we're going to test from negative 1 to 1. That's right here. And then finally, we're going to test from 1 to infinity. And we're testing the second derivative. So when we do that, if you plug a value that's less than negative 1 into the second derivative, so like negative 2, you will find that that value is greater than 0. In other words, it's positive. And if f double prime is positive, then it makes it concave up. So this function is concave up to the left of negative 1. By the way, same thing happens on the values over here to the right. Turns out that f double prime is greater than 0 when you pick numbers bigger than 1, like 2. But when you pick in the middle, that's this part right here, if you pick a number between negative 1 and 1, like 0, when you plug that into the second derivative, and remember the second derivative right here is 36 quantity x squared minus 1 over x squared plus, the bottom is going to be 3 to the third, which is 27. The numerator is going to be negative, so it's going to be negative 36 over pi, so it's negative. So this is negative, which means it's concave down right here in the middle. And that's how we can now answer our question. So the conclusion that we can draw is right here. I didn't want that to be that color, but we'll go with that. The function is going to be concave down. In fact, let me write my answer. Here's how you would write your answer if this had been a test question. You would say that it is, you'll see me write this a lot, concave up. So CC with an up arrow. It's concave up from negative infinity to negative 1. Union from 1 to positive infinity. Okay, so that's where it's concave up. And then it's concave down, so CC down. And that's going to be concave down from negative 1 to 1. So this is how you could write your hand short, or here's how you could write it shorthand. Okay, and the reason, for example, if I asked you to justify why it's, let's say, concave down from negative 1 to 1 is because f double prime is less than 0 on that interval. Okay, so let's talk about points of inflection. If the tangent line to the graph exists in such a point where the concavity changes, in other words, you have a tangent line, you have a tangent line, you have a tangent line, but the concavity changed from up to down in this example, from down to up in this example, from up to down in this example, we call this point a point of inflection. You'll see me often refer to it as a POI, a point of inflection. And here's our definition for a point of inflection. Let f be a function that is continuous on an open interval and c be a point on that interval. If the graph has a tangent line, which is what we just mentioned, then this point is a point of inflection if the concavity changes from upwards to downwards or vice versa. Points of inflection. If c comma f of c, that means basically some x and some y, is a point of inflection, then either f double prime is 0 or f double prime does not exist. This is similar to when we talked about like critical numbers. Except now we're talking about the second derivative. So let's see if we can actually find a point of inflection. So if we go back to this theorem here, I'm going to erase all of this ink. If we look now at this theorem, and let's see if we can figure out if we've got some points of inflection. First of all, you'll notice that this function, I'm using a pretty easy function here. We're going to go ahead, it's continuous and differentiable for all real numbers. So let's go ahead and find the first derivative. So f prime is going to be 4x cubed minus 12x squared. Let's go ahead and find the second derivative. So that's going to be 12x squared minus 24x. We could factor that. Now the question I have is when is this 0 or D and E. When is it 0 or D and E? Well, it's never D and E, so it's when is it 0? Well, it's going to be 0 when x is 0 or 2. So if I put 2 into that, that makes that 0. If I put 0 into that, that makes that 0. So f double prime is equal to 0. So the possible, and this is the key word, possible. And let me make sure I emphasize this. This is something I have to do a lot with my geometry students. Notice this theorem says if it's a point of inflection, then either this is true or that's true. This is an if-then statement. So just because this is true does not necessarily imply that it's a point of inflection. You still have to check. Okay, so we figured out that x equals 0 and x equals 2. Those are possible points of inflection. Let's check. We're going to play the same game we just played. We're going to do some test values. And we've got the following. So we've got x equals, remember, we're going from negative infinity. Actually, I don't need to write that because we have it written here already. I'm sorry. So let's go ahead and test from, I'm going to go to my highlighter. Let's make sure we're on yellow. Negative infinity to 0 because 0 is one of them. We also need to check 0 to 2, and we need to check from 2 to infinity. So what's a number that's less than 0? Well, -1 might be a good one. And when you check that, when you plug that into the second derivative, right here, if you plug -1 into that, you're going to get -12 times -3, which makes that positive. Second derivative is positive, so it's concave up there. If we pick a number between 0 and 2, like 1, it turns out that the second derivative is less than 0, so it's concave down there. And finally, if we plug a number that's between 2 and infinity, that'd be like 3, for example, it turns out that it's concave up. So look at our picture over here on the left. This is the actual function. You can see it's concave up here, it's concave down here, and it's concave up there. So that makes 0, 0 a point of inflection. 2, -18 is also a point of inflection. All right, last thing, the second derivative test. This is probably the most misunderstood theorem from this chapter, and I don't think it's that complicated. I think the name gives you a lot of information, but I think people think that this is how we determine concavity, and it is not. I will refer you back to the objectives for this course, or for this lesson. The very first slide in this presentation, the third objective is to use the second derivative test to find relative extrema. So that's what this is doing. This is for finding relative extrema. You should probably add that to your notes. This is to find relative extrema. Here's how it goes. Let f be a function such that the first derivative is equal to 0. By the way, if the first derivative is equal to 0, we know that's a critical number. And we need the second derivative to exist. If these two conditions are met, then here's what we got. If f double prime is greater than 0, it has to be a minimum. Now let me stop there and kind of explain that. So what we're saying is we've got a critical number. And by the way, it's a horizontal tangent line. So if I have something like this, here's my function f, and then right here at this point, I'm going to have a horizontal tangent line, right? A horizontal tangent line there. By the way, what's the concavity there? Well, it's concave up. In other words, f double prime is greater than 0. So guess what that had to be? It has to be a relative minimum. Kind of makes sense. Kind of makes sense. A common mistake, though, students see, they see this here and they think concave up, so they think it must be a maximum because they think up is max. But remember, it's concave up. That means it has a bottom point, so this is a minimum. Let's go ahead and finish this out. If f double prime is less than 0, which means it's concave down, then it has to be a relative max. Now let me emphasize this third thing here, this little final point here. If f double prime is equal to 0 for C, then the test fails. In other words, you cannot use it. So if you did the second derivative and it turned out to be 0, you have to use the first derivative test. So make a note of that. It doesn't happen very often, but that'd be a good test question or a good AP exam question. So let's see an example. But let me make sure I make a point here too with these examples. You'll notice that in the examples I've been doing this last couple presentations, I've been trying to stick to fairly innocent polynomial functions. I haven't done a lot of trig or transcendental like e to the x or trigonometric functions, just because I'm trying to make sure that you guys don't get hung up on the derivatives. So we want to use the second derivative test. Now here's how it works. First thing you want to do is figure out what your critical numbers are. So how do we find critical numbers? Well, we set the first derivative equal to 0 or d and e. Now in this case, we're really only interested in setting them equal to 0, and you might not be sure why that is. Well, that's because the second derivative test requires the first derivative at that value to be 0. So we're only interested in it when it's 0. And we can see here, when is this going to be 0? Well, when it's 0. When is this quantity going to be 0? Well, when it's negative 1 or 1. Okay, I'm going to erase my markings on here. So there's our critical numbers. We have our critical numbers negative 1, 0, and 1 based on the first derivative. Now, here's what we do from here. What we're going to do is we're going to take these three values and we're going to plug them into the second derivative. So the second derivative, that is the derivative of this, turns out to be this right here, which could be factored into this. And we can plug these values into this and see what we get. So I've got that information now here on this slide. Remember, the first point was negative 1. So when you plug negative 1 into the second derivative, and I will just remind you that the second derivative is right here. So if we plug negative 1 into this, we will get 30. Oops. Sorry, that's going to be a hot mess. Fix that. Let's go back to ink. So we're going to get 30 times negative 2, and then let's change that to red, times negative 1 raised to the third plus, and then another negative 1. So what's that going to give us? Well, that's going to be 30 times negative 1 to the third is negative 1, so this is going to be positive 2, then minus 1. This is clearly greater than 0, right? In this case, I think it's going to be 30. So that's greater than 0. 30 is greater than 0. So that implies this has to be a relative minimum because it's concave up. Relative minimum. Now, the second value that we had was actually 0, but I'm going to go to the third one, which is when x is equal to 1. When we plug 1 in, we get less than 0 for the second derivative, so that makes that one a relative maximum. Okay, so everything looks lovely. Now, let's go back to this middle guy here when x is 0. It turns out when you plug x equals 0 into this second derivative, you're going to get 0 plus 0 times 30, which is 0. That means that the second derivative test fails. Since the second derivative test fails, you cannot use the second derivative test to determine if this is relative min or relative max. You would have to go back to the first derivative test to determine that. And I have that written right here. Here's the graph of the function that we just looked at. It turns out, like we said, when x was negative 1, that was a relative min because it was concave up there. Turns out when x is equal to positive 1, it was a relative max because it was concave down there. And it turns out, and this is probably the most important part in terms of making sure we understand the theorem, at x equals 0, it turns out that there is no sign change in the first derivative. It goes from increasing to increasing. So therefore, it is neither a relative min or a relative max. And that will end our presentation. Thanks for your attention.